So, we are introducing another new term, mesomeric or resonance effect. So, we will see the difference. Does it have anything between mesomeric and resonance? The first one is this resonance effect actually works in the case of conjugated systems. Lone pair or pi electrons are also involved, because that is what we say conjugated systems require. The resonance structures actually works in the pi system. So, pi means either lone pair will be involved or pi electrons are involved, and this is actually a permanent effect, and it is a qualitative measure to explain some of the observed phenomena. It is much stronger than the inductive effect. The hybridization of the atoms does not change. So, these are all some of the important facts about resonance effect. In fact, the term mesomerism is often encountered in German and French literature, but not in English literature. The term resonance is more frequently used by the English people. When we write the structures, those who use the term mesomeric tend to use Lewis dot structures, whereas people who use the term resonance use partial single bond and double bond structures. Of course, these are some of the conventions people use, but there is no difference if you use the word mesomeric or resonance, because these two are synonyms. And scientifically, there is no difference between these two terms. Based on the pi bonded electrons, movement between the conjugated system and to a particular group, that is plus m or minus m, is assigned. So, basically what we are looking for is, when we say mesomeric effect, basically we will be referring that as a plus m or minus m effect. Plus m means donation, minus m means withdrawal. So, that is what we have to say. So, when the electrons are donated, so whenever there is a donation, that is called plus m here. Some examples include amino groups. Here we see an example of the amino group. So, that is what we have given it as a different color. So, how the electron donation takes place? Nitrogen is having a lone pair. So, this lone pair is donated between the carbon and the nitrogen bond, and this double bond is now shifted towards this particular carbon. So, which becomes a carbon ion or a negative charge. So, there is a carbon nitrogen double bond that is formed, and of course, now you will be asking, sir, is it a acceptable structure for a resonance structure? Because we know charged structures should be avoided for resonance, 1, and 2, the nitrogen is actually having a positive charge. Basically, when we draw the resonance structures, we generally use the negative charge on the most electronegative atom, but here we have drawn exactly the opposite one. So, how this structure is an acceptable one? Actually, this kind of notations are given to explain some of the reactions what we actually see. Especially in the case of Hammett equation, we will be encountering these kind of things while we explain the orthopara directing effect of the nitrogen group, that is the amino group. So, there we will be invoking these kind of resonance structures. And the next one is, when the electrons are pulled by the group which is called the minus m effect group. Say for example, here oxygen is more electronegative, so it pulls the bonded electron towards itself, making it a negative charge on oxygen, and the carbon becomes positive charge. So, these type of groups which actually pull the electron towards itself are called minus m groups. Some examples are nitro group, cyano, acid halides, sulfonic acids, aldehydes, amides, COR. That means here we had given a ketone like group. So, these are some of the examples of minus m effect groups.